Hi, this is going to be 3004 prep for test number 8. This is 2018. We're going to look at the 2017 test, and this is the stuff from chapter 18 in the textbook. So transient heat conduction. So we have a question here. Valerian steel smithing involves a process of heating and quenching Valerian steel, and it's we've got its material parameters there. Suppose during forging, a soon-to-be greatsword has a shape of a rectangular prism with dimensions of this. If the steel is uniform that, when it's placed into a large pool of that temperature water, subjecting it to a convection coefficient of this, determine the temperature of both the center and the center of one of the flats of the blade. So the part that is 1 centimeter off from the center in this third dimension here. After 50 seconds of quenching using a series of different approaches. So first the lumped system approach, then an infinite plane wall approximation for the kind of thickness direction here, the 2 centimeter direction, then a pair of infinite plane walls for the width direction here, the 10 centimeters, and then a combined trio of infinite plane walls considering all 3 dimensions, and comment on the accuracy of these approaches, explaining which of the relevant approximations are justified in light of a typical 10% error in the convection coefficient. So let's start off with the lumped system approach. And to do this, we're going to need to go to the material at the beginning of chapter 18 there. So lumped system approach, we calculate a BO number using the characteristic length as the volume over the surface area. Then the BO number really just tells us whether it's justified for the lumped system approach. The calculation itself doesn't have anything to do with the BO number. So we're just going to say that the temperature relative to the free stream temperature of the fluid is going to be the initial minus the free stream times this exponential e to the negative HAS over mass times Cp, the heat capacity multiplied by the time. Okay. So let's get ahead. Let's go ahead and calculate all of that. We've got our computer algebra system here. You could use any calculator you like. And we're going to substitute in the material parameters. And the dimensions. Then we're going to calculate the surface area and the volume. So surface area would be 2 times Lx times Ly plus Lx times Lz plus Ly times Lz. And the volume is going to be Lx times Ly times Lz, which means the mass, we don't actually need to output what those are. The mass is going to be equal to the volume times the density, and the heat capacity, or I guess, okay, so we're good to go here. We can calculate the BO number for the lumped system approach, which would be based on the characteristic length which is the volume divided by the surface area. And the BO number that we would get would be the characteristic length times the convection coefficient divided by the conductivity. So that's defined up here, characteristic length, convection coefficient divided by the conductivity. And so, we need to put in the convection coefficient. H is 1,000, I believe. Is that right? H is 1,000, yep. And we can also put in the final time is 50 seconds. And the free stream temperature is 0. The initial temperature is 2,000. Okay. So there's our BO number. Now the BO number is larger than 0.1, so probably the lumped system analysis is not quite justified, but it's not that much larger than 0.1, so we don't expect it to be completely off. Anyway, let's go ahead and calculate the temperature. So that comes from this calculation at the end of 18.1 here, where you just solve this first order differential equation and you find that the temperature goes exponentially in time according to this exponential of -h surface area divided by mass times heat capacity times temperature. So we've got temperature is equal to T inf after we rearrange plus Ti minus T inf times this exponential. E to the -h times AS divided by M times Cp times T. And we're also going to need to figure out what M is. So now that we found the volume, oh, I guess we did that already. Okay, we're good. So volume times the density, and we've got Cp, so everything should be good to go. Okay, so it looks like the temperature after 50 seconds is 262 degrees. So this certainly is lower than the initial temperature, and then we can just test some things. So if we put in a time of 0, then we start off at 2000, and if we put in a time of 500, we should get pretty close to 0. Yeah, quite close. So let's just go back to 50. It looks like it's going in the right direction, decaying exponential from this function. Okay. So the next part is this infinite plane wall approximation, only considering the length in the 2 centimeter direction. So for this part, we're going to go over to the end of 18.2, or maybe the kind of the middle of 18.2 perhaps. And the plane wall approximation is this first set. So we get our dimensionless temperature, theta, is the sum of this series, which has coefficients that are based on the Biot number and the Fourier number, where now the Biot number is calculated using the half thickness of the wall. So the characteristic length for this one is going to be based on the length of the thickness of the sword here divided by 2. So we'll go and suppress some of these things from before that we don't need anymore, and we'll go the maybe 1 degree approximation. And so the length is going to be Lz over 2, and then we're going to use that to calculate the Biot number. So the Biot number is going to be L times h over k, and we'll also need to figure out the Fourier number. Maybe we'll call this T lumped. Yeah, so the Biot number is that, and then we've got Fourier number, which we're going to need alpha for, and alpha doesn't depend on which approximation we're using, so we can put that calculation kind of at the top. It's k over rho Cp. Okay, that's thermal diffusivity. Now we've got the pieces of information that we need to figure out the Fourier number, which is alpha over L squared T. So that's tau is alpha over L squared T. So with T 50 seconds, we've got a Fourier number, Biot number of 0.4 and a Fourier number of 4.16. Okay. So the Biot number, with that information ready, we can go and figure out that. Okay, so because the Fourier number of 4 is bigger than 0.2, we're okay to use just the one-term approximation. And that means we can substitute in, we just need to figure out what lambda 1 and A1 are. If we didn't have a, if this wasn't a test, then we could just use a computer to solve this, where is it here? This implicit equation here for lambda, solve this numerically for what the lambda is that makes it work for the Biot number, and then substitute that in here and calculate what this coefficient is in front. But to save time, we can also use the table. So the Biot number of, I think, was it 0.2? Biot number, 0.4. Biot number of 0.4 tells us what lambda 1 and A1 should be. So lam1 is 0.5932 and A1 is 1.058. Okay, so now that we got that, we can go in here and calculate what the dimensionless temperature is. So theta theta z at the center is going to be A1 times e to the negative lambda 1 squared times tau. And then we're going to have x is 0 at the center. So we're substituting in a 0 for that, so we're all good. Okay, so that's theta z center. And to find theta z at the edge, we're going to take theta z at the center, and then we're going to multiply by cos of lam1 times 1. Okay, so theta z center and theta z edge give us this thing. So 25 or so, 24% of the original temperature is left there, and 20% of the original temperature compared to the free stream temperature. So this gives us, again, information of how we can figure out that temperature, and the calculation is kind of similar to the lumped system calculation. So T Z cent is going to be that times theta z cent. Tz edge is same thing, theta z edge. So you multiply those thetas by the, so remember that this is the dimensionless temperature, which is the temperature minus the free stream temperature divided by the initial temperature minus free stream temperature. So rearranging that, we can calculate what these temperatures are at the center and the edge. Okay. So the next part asks us to use a combined pair of infinite plane wall approximations, and this would be using also the 10 centimeter width part. So from the center of this to the edge would be 5, and we're going to find an approximate temperature for that. Let's call that the y coordinates. Maybe we'll say 2 deg approximation, and now the L would be Ly over 2. Then we'll have some similar kinds of calculations as what we had before. So we'll say, I'll just copy a lot of these things down. So okay, we've got Ly over 2. Then we're going to use that to figure out the Biot number and the Fourier number. Okay, so Biot number now is 2. The Fourier number is actually a little bit less than 0.2, which means the one-term approximation is not strictly justified, but we definitely don't have the information to do a 2-term approximation on the test, so let's just kind of keep that in mind, but try the 1-term approximation anyway. Okay, so we've got, we need to relook these up for the new Biot number of 2. And if we go back to our notes here, then a Biot number of 2 gives us a lambda 1 of 1.0769 and an A1 of 1.1785. Okay, now we're not going to use this to recalculate theta z at the center and theta z at the edge. No, we're just going to figure out theta y at the center. And theta y at the center, oh, I guess I shouldn't have deleted that other part. Theta y at the center is going to be calculated with the same kind of formula as we calculated theta z before, except now we've substituted in the new Fourier number, the new lambda 1, and the new A1. So this is because we're just using we're calculating things in this question at the center of the flat of the blade, and in the width direction, that's still in the middle. That's the center as far as this one's concerned, but we're on the edge as far as this one is concerned, or possibly the very center as far as this one's concerned too. So that's because we're finding both the temperature at the center and the center of one of the flats. Okay, so that's theta y cent. Yep, and then we'll find the total temperature at the center by using a combined calculation. So we'll take the z dimensionless temperature in the center, and then we'll multiply that by the y-based dimensionless temperature in the center, and then same thing at the edge in z and the center of y. So this should be doing the new temperature calculations. Theta y cent is now very close to 1, because after this amount of Fourier number, we haven't had much time to cool down from the original center temperatures, from the original temperature of the object there in the width direction. So most of the reduction in temperature comes from that 1 centimeter distance it has to move, not from the 5 centimeter distance it has to move, and that kind of makes sense. The very last part is going to test the limits of these approximations by looking at the 1 meter distance. So we were at too low of a Fourier number to use the one-term approximation before, and now we should really be in trouble. So let's try this out for the 3-term approximation. So the 3-term approximation, the 3-degree approximation. So where we're looking at the heat transfer in all 3 dimensions. So now we're going to say that the length is equal to Lx over 2, and the Biot number again is L times h over k, and the Fourier number is alpha times L squared times t. So this time we find a Biot number of 20, and that's not so bad, but the Fourier number is very low. So we'll kind of truck forward anyway and see what the consequences of this are. So going back to the tables, Biot number of 20, right? Yeah, 20. 20 gives us a lambda of 1.4961 and an A1 of 1.2699. So the problem with that is now if we were to figure out what the theta z would be, or theta x, I suppose. X is the last dimension, the length of the sword. It would be A1 times e to the negative lam1 squared times tau, as usual. But this gives us a theta which is larger than 1. And that means that it's actually heated up at the center compared to what it was before. So this is completely ridiculous, and is because the Fourier number that we have is nowhere near greater than 0.2. So we're really not justified using only one term of the approximation. So what should we do? Well, the best we can do in this situation, short of doing a more detailed calculation that incorporates more than one term, is to say that in fact theta x center is just going to be approximately equal to 1. So if we've waited such a small amount of time that we haven't even reduced, that we've ended up with a calculation that puts it at a bigger number than 1, then we should just set it equal to 1, so that we at least aren't increasing the temperature there, and say that the conduction down the length of the sword doesn't affect things, and we end up with the same temperatures as before. Finally, the question asks us to comment on the accuracy of these approaches, explaining which of the relevant approximations are justified in light of a typical 10% error in H. And if we look at these, we see that the difference between so the most accurate one should be the very last one, but we said that actually gives us exactly the same temperatures at the edge and the center, at least to within what we can calculate using only one term approximations, as the conduction down the width and out the side did. So the 2-degree calculation gave us the same answer as the 3-degree one. So we definitely can ignore the conduction down the length of the sword for this time range. Okay, now can we ignore the conduction down the width? So that would take us to going to 404 and 488, and considering that H has a 10% error, these are kind of within 10% of each other by a fair bit. So in fact, we could even justify using these temperatures as our estimates of the temperature after 50 seconds rather than these ones. The lumped system approach, though, is really not so justified. So it's fair to say that this is our best estimate of what the temperatures will be. These ones are within the error. So although this looks like a better estimate, considering the errors in H that we're dealing with, we can't really declare that this is necessarily justified to bother with the two-term approximation compared to just using one term, though it does seem like the lumped system approach is not that valid for this. It really underestimates the temperature compared to what we calculated using the other approaches. Okay,